Hello everyone interested in the theory of machine and deep learning. So let's continue our journey. And previous time we have talked a lot about the probabilistic connections of the key concepts of classifiers, for example. It was mostly cross entropy, but actually there are a lot more different loss functions. And how are they usually constructed? What is the idea behind it? And how it is connected to the concept of representation learning? Let's deep dive today. So today we are going to first to jump into the representation learning. What is it? Then we'll look into FaceID task. And go step by step for the historical overview of this task. Why it's important? Just because this FaceID task is a good example where we can see step by step how the loss function approaches were evolved. And talking about specific approaches, we will look into softmax loss and its variations, then Euclidean metric loss and its variations, and finally into angular loss and its variations. So, representation learning, but representation learning is not the, how to say, first and initial approach. Initially, the whole machine learning machinery was done on top of feature engineering. Or like multiple words can be used. It can be feature extraction or feature discovery. And what is it? This is the mapping f from some arbitrary object, all lowercase, in O capital. So O capital is the set of all objects, and some object is like all lowercase. And this mapping to some unified feature space representation, x lowercase in x capital, which is a subset of some RD, so as f maps O capital to x capital. So we're having this mapping between objects and their representations. Objects just some, I don't know, some space. These objects can be very different, and probably this object do not have any, I don't know, unified representation, but x is quite uniform. So every x from some RD, for example, here, and we can write it as a vector, so we can use some mathematics behind it. Suppose we have m lowercase object, so we can construct the training dataset xm, as in previous lecture. And on top of this representation, we can learn usually a linear, but not every time, but usually. This classifier, and we in the previous lecture we called it a lowercase of wxm, and if you're talking about the linear classifier, this is sort of sign of g of x comma w, and usually this discriminant function g is just a dot product or scalar product of x, of in our case x is a representation of the object, and the vector of parameters w. And usually we are using this notation of angled brackets as for dot product. Or also it can be used as x dot w. This is the same. This is a feature engineering. So somehow somebody needs to find this mapping f. So this f usually was done manually by some domain experts using some, I don't know, different approaches. For example, we can include more features, or we can include less features. These features can be semantical, usually semantical. For example, if we are talking about the palm itself, it can be a number of fingers, it can be, I don't know, the shape of the palm, the inclination, etc., etc. But it's quite difficult to construct for every task this function f, and we also would like probably we don't know in advance whether this mapping is optimal. And here these concepts of representation learning comes onto the stage. The main goal here is to have object representations, this X, to be rich and descriptive. Representations of objects of the same class should be as close as possible in this feature space, and when we are talking about close, this is subject to some metric, for example Euclidean metrics or some other, but let's use the simplest example as Euclidean metrics. And also we would like for representations of objects from different classes to lie as far as possible from each other, again according to some metrics. So if we have for example representations of objects of class A of two objects, we would like for these representations to be as close as possible, or probably ideally to be merged into some point. But if we have the representations of two objects, one from class A and another one from class B, it would be better for them to lie far away, probably on the distance not less than some threshold data, for example. And sometimes these initial features x in x capital are just not suited enough for this task. For example, you don't have either this property or this property, and let's just remember that x is just some mapping that probably has been done by human experts or oops. Okay, no, doesn't matter. By human experts or probably some automatical feature extraction, which probably is not optimal or just doesn't cover all the needed properties of the object. So we would like to use better representations. How to do it? For this purpose, probably we need some additional mapping H from this initial feature space X capital into some additional representation space R, which is a subset of Rn, well, like H maps X to R. And the learning of this additional mapping H, this is what is called representation learning. And this is a simple illustration. Suppose we have objects consisting of either dogs or cats. And even cats and dogs can be of different color. For example, dogs can be blue and can be black. And dogs, this is dogs, and cats can be red or also black. And in the initial, these are objects, real objects, but we have some representation. For example, this is, for example, axis x1, this is axis x2, and for these initial representations, f, when we project this representation onto this 2D plane, we can see that there is no clear clusterization, separation of these classes. But suppose we can use some additional algorithm H, and here in case of this H we have deep neural network that can map the initial representation into the better one. And here we could have the better representation, so we have clusters of blue dogs, cluster of black dogs, cluster of black cats, cluster of red cats, and we have some outlier, but that's okay. It is much better than it was before. And yeah, the goal of the representation learning is to find out this mapping function h in such a way that it could provide some semantical mapping. So we can clearly separate based on the classes interpretation. And here classes are just the species and the color, for example. Okay, let's move further. Suppose we have the initial representation x in RD, and it is done by some function. And this function, let this function be, in our case, neural net. It doesn't matter. And this representation h of x is from Rn. So initial representation was of dimensionality d, but then we'll jump into the dimensionality of n capital. And its equation, for example, whether d should be greater than or equal than n, or vice versa. Sometimes we need to decrease an amount of dimensions. Sometimes we need to increase it. It's really dependent on the task. But for example, when we are talking about images, initially, for example, suppose we have 100 by 100 pixel images, and like even like one color, we could have 10. This image can be represented as a vector of 10,000 elements. So d in this case equals to 10,000. But usually we would like to have some representation, some embedding of this image into the, for example, lower dimensionality. For example, if we have here this 100 by 100 and black and white or like grayscale image, it means that d was 10,000, but we would like to compress it into the vector of, for example, here n capital of, for example, 512. And our goal is to classify x based on its representation, based on its new representation h, into one of the k capital classes. And a is composed of 0, 1, etc., k minus 1. So k can be 2, can be 3, can be 10,000, can be 1 million. It depends on the task itself. In this case, we need to project the learned representations into k logits. So later we can use these logits as the input to softmax. Remember, our softmax, this is some mapping that maps any vector into a probability vector. And use corresponding softmax loss to produce probabilities. And logits are usually defined by with simple formula. It just W, this is a projection matrix of the size k multiplied by n. H is our representation, and plus some bias term is just RK vector from RK. Usually it can be even 0. So it's just a multiplication of initial representation to some matrix, and this matrix has k rows. And our probabilities are just Q. This is softmax of L, and L is equal to W multiplied by H of X plus B. And linear classifier here is argmax over C in Y of softmax of L and its Cth output. This is equivalent to argmax over C in Y of the dot product of WC and H of X plus bias term, where WI is the ith row of matrix W. It's quite understandable. So yeah, so we have this the whole machinery of softmax, but actually again we have here this very simple linear classifier. A couple of words about neural collapse. This is quite funny story because it was the ideas from these papers, related papers, were known before, a long ago before, but they were mostly used empirically, based on some empirical observations, but there were no theoretic proof, and only in 2020 and 2021, as you can see here, the proofs have been provided. So what is it? What is neural collapse? Recently, it was not found. It was it was proved that in the terminal stage of training of any deep learning classifier with cross-entropy loss, remember cross-entropy, in the overparameterization regime, means that the number of weights inside the model, for example, the number of weights inside neural net, is much bigger than the amount of training data samples. When empirical risk is already zero, but empirical risk approximation is not, yeah, that's important, because empirical risk, this is a number of errors, but empirical risk, what we have? We have empirical risk, this is the upper bound of empirical risk. So sometimes we could have, for example, the amount of errors equals to zero, and the empirical risk approximation doesn't equal to zero. So this is specifically the case. For example, it is, I don't know, some alpha bigger than zero, and here empirical risk is equal to zero. The average representations h of x for each class tend to group around each class center. It means that doesn't matter what the example from some class, its representations would be very, very close to each other, and as a consequence close to the class center. And much more important, these class centers of representations will coincide up to some rescaling factor to these classifiers, and W, this is the row of the projection matrix from logits, from representations to logits, and this is what is called linear classifier W, and they would coincide with it, and this is super cool. And what has been known before, as I said, empirically. So when we can, for example, when we don't know, when we start to train the linear classifier, we can initialize this classifier Wi with the class center for the classes, and then we can fine-tune it. And this was known before for a long time. This phenomenon is called neural collapse. Initially it was defined for classifier, but later, like a year later, it was proved for the regression task as well. Yeah, and here you can see this effect. So you can see here 3 different colors. We are not going to talk about ETF, and you can consider reading the initial paper. But what is important here, this is like blue dots. These are representations. And they tend, here we have 3 classes, class 1, class 2, and class 3, and they tend to be concentrated around each center, and center, this is the center. And the red one, this is the classifier W3 in this case. This is very important thing. This thing would be used like anywhere in your career in deep learning, for example. So please be careful. Please remember this important fact. Okay, we consider this task a little, this neural collapse for some following slides, but not right now. But let's remember it for now. Okay, now jump into face recognition. For face recognition, basically speaking, we have two subtasks, main subtasks: verification versus identification. In verification, this is the simpler task. We just need to check if the input face is the same as the original one or template. And identification, this is the task to find the identity from some data set full of some IDs. It could be like not one, it could be like million of different IDs. Or if we cannot find this identity in our data set, we just need to report that this input ID is absent in this data set. And what we have usually on our smartphones, and this is called Face ID. It's not Face ID, it's actually verification. Face ID, this is identification. And Face ID is much harder than verification. We just not to compare with one face, we're comparing with a whole bunch of different templates. Now the number of IDs in this ID dataset can be of the order of billions, and the training dataset can be on the order of millions, tens of millions, or even more of IDs. And why we are talking about Face ID? Because of these numbers, billions and millions, compare, for example, with the usual MNIST CFAR data sets. They have, for example, 10 classes or 100 classes. It makes this Face ID one of the most challenging applications of representation learning techniques. And that's why we are going to look into the history of Face ID losses as the approaches how we can tackle the problem of representation learning, as well as losses on top of it. The common pipeline here is depicted. Yeah, we have the input image, then we have the detection model that detects the face itself on the image, and also some predefined key points. It could be eyes, nose, mouth, eyebrows, etc., etc. Then we are transforming to some predefined places. We have the predefined places for these key points. And you can see here, like here was a straight line and just inclined a little bit. Then we are cropping the face itself, this normal position of the face already transformed. And then we have here deep neural network, which is feature extractor. And this feature extractor just provides us some representation. In this case, in just 128 dimensions, but it doesn't matter. And based on this representation, it just, for example, 128 units, we can make on top of it a lot of tasks, like, and try to solve them. For example, clustering, similarity detection, classification, face ID, face verification, emotion recognition, etc., etc. And everything will be done on top of this representation. A little bit more formally, this pipeline, without fine-looking images of Sylvester Stallone, but basically the same. So we have initially face location, size, and pose. We have face detection. It provides us, yes, like specific face location, size, and pose. Then we do this alignment. As I said, like we have these key points, and we just transform into the specified places. So we could have these aligned faces. Then we have this feature extraction. It provides this feature vector, and we have the face data sets that have, for example, 1 million of templates, and we need to have the additional step here to match our feature vector with this face data set, and then we can report either we have found the specific face ID or not. And if you're talking about neural nets, usually we have two neural nets. For face detection, it's called face detector or face det, and for feature extraction, when we're extracting this representation. And usually it's called FaceID. Yeah, and let's provide a little bit more formalism around FaceID task. Initially, task formulation as a face classification. And that's important because we just need to assign an input to some predefined class. Predefined, it means that even before solving the task, we know, for example, we have these 10 persons, and we just every input will be classified to the first, second, etc. 10th person inside our data set. We don't have the open data set. It is closed data set, closed set recognition. We already have it. But later, the task evolved to a more realistic setting, which is called few-shot learning. Very similar, but classes are known only during inference and not during training. So we are basically speaking, we are training on one set of IDs, but need to, during the inference, during the testing, work on top of other sets of IDs. Anyway, both are based on a simple classification task, and that's important because almost everything today will be concentrated around classification. And FaceID task, more formally, so classification. So given k capital classes or IDs and input face x, we need to find the closest class as argmax over I in the set composed of 0, 1, etc. k minus 1 of the dot product wi and h of x plus some bias term bi. And for identification, the task is a little bit harder. So given the data set of m ID representations, h capital, composed of h0, h1, etc., hm minus 1, and input face x, we need to find the closest ID based on some similarity function s, which maps two inputs from Rn to R. And this similarity function is defined as argmax over I in set composed of 0, 1, etc., m minus 1 of s of h of x and hi. Or we need to report the absence, because sometimes we don't have the specific ID in our data set which we compare against. And we need to report this absence if very simple criteria here is used. If maximum over I in the set composed of 0, 1, etc. minus 1 of s of x, comma hi is less than some threshold theta. So basically speaking, we just need to find out the class which provides us the bigger similarity, but if and only if the similarity is greater than or equal than some threshold theta. How to find out this theta? This is the separate task itself. Sometimes it's just hyperparameters which we can find based on some cross-validation procedure or something like that. Yeah, let's jump into this historical overview of different approaches to FaceID, and here it's nice illustration from some survey. You can click here. This is from arXiv, a nice paper. So basically speaking, we have here 4 approaches with different colors. Red ones is the first one, where we have the predefined amount of classes which were used for our classifier. So this is simple and pure classification task. The green one this for metric learning based approaches. The blue one, this is for normalization approaches, and the green one, this is for angular based approaches. So yeah, softmax based, this is metric learning, these are normalized, these are the angular. And today the scope of the lecture would be concentrated about these three approaches: softmax, Euclidean metric, and angular. And as you can see here, like this is like the evolution, but also there were some approaches how to add this, as you can see here, the blue one, some normalization here or here, and finally, as it can be called the newest era, it's mostly marginal improvements, and I wouldn't, this is my personal opinion, I wouldn't say that we have any breakthrough after angular losses, to be honest. Okay, let's start with the softmax loss. In FaceID community, softmax or SM loss, this is the same as cross entropy. Like, remember, what is it? This is minus sum of minus log p of xi. Oops. So softmax loss was the first loss type used for the FaceID task, because it's the simplest. This is the original formulation of the classification task. What we need to do, we need to use cross entropy, because this is the same as maximal log likelihood estimation, like remember the previous our lecture. And why it is important? Just because it just makes the one-hot encoded probability of ground truth to be as close as possible to the predicted ones. So very obvious, very natural. And some examples are here called deepface or deepid, and you can see here that this approaches has been done already in 2014, and just remember that the whole deep learning revolution started with AlexNet in 2011-2012, so a couple of years after. And this deepface, as I remember, this was the approach from Facebook that they applied on their social net. In comparison to usual classification, where we can have like 10 or 100 classes, we have here a large number of classes, probably much bigger. What is class here? Class here is a person ID. For example, person 1, person 2, person 3, person 5, and usually it's about from 10 to 100k. K means like 1000 classes, and can be even more, especially when we are talking about the surveillance applications. For example, on the scale of the city, you'll need sometimes millions of IDs. And intra-class variation can be bigger than inter-class difference. That's important, and that's a pity. So what is intra and what is inter? If you, for example, don't know what does it mean, intra-class variation means the variation inside one class. Intra means inside one. And inter-class difference means that the difference between different classes. That's the meaning of inter versus intra. And yes, this is illustration of application of softmax logs on MNIST classification. MNIST is a classification of 28 by 28 grayscale images, and the images of digits from 0 to 9, so 10 digits. And yeah, this is the output when we just classify it, and we can see and we can project the representations into the 2D plane and with different colors. For example, it can be 0, it can be 1, it can be 2, 3, etc. And this is the problem. So suppose we have two classes, class 1 depicted by the blue dots and class 2 depicted by the red dots, and the biggest intra-class variations here is d1 for the blue one class and d2 for the red one class, but the minimal distance between two classes, between examples of the different classes, d12, and you can see here that d12 is less than the intra-class variations, or minimum of d1 and d2. And this is the softmax separation hyperplane. So this is the problem. So for example, why it is a problem? Because probably sometimes you can just you would just need to understand the new input, whether it belongs to the D1 or to the class 1 or class 2, but it can be closer to class 1, but actually it is inside class 2. So, or vice versa. And this is a problem, and seems that most of the work that we are going to talk today was how to solve this problem. Okay, the first approach is basically the normalization-based one. It is called L2 softmax. Please do not mix with L softmax, because L softmax is a much more advanced approach, which we will look at today later. So, L2 softmax. Often cosine similarity is used as a similarity function, as I talked before. This is the dot product of hx and hy between, for example, face images x and y. And it is divided by the norms of these representations. And so basically speaking, this is the cosine of hx, hy. Just if you remember what does dot product is. And it causes some discrepancy between training loss or softmax and testing procedure, because for testing procedure we are looking into this similarity, but for when we look into the training loss, it's very different. It's just cross entropy. It's not the same. And it was also empirically shown that the best results for the representations can be provided when we these representations have high L2 norms. This norm. So the idea, let's introduce some scale layer h prime on top of the initial representations h of x with one learnable parameter alpha, so as h prime of x equals alpha multiplied by h of x divided by the norm of h of x. So in this case, one can clearly see that the new norm is equal to alpha. And the training loss, in this case, softmax loss, just remember the derivation as we did the previous time, in just minus 1 over m, the sum from I equals 0 to m minus 1 of a log of x e to the power of dot product of w yi. Yi means the correct class. Oops, sorry, let me do it better. The correct class for the input xi plus some bias term again from the correct class, and it is divided by the sum over all classes j. But we have the this specific layer in such a way that we have the norm of this h prime equals to alpha. Yeah, and this is the illustration of this new layer. So initially we have the input, we have some normalization layer, just divide by the norm, and then we have here the scale layer, just multiply by alpha. What is important, so we can have this parameter alpha learnable. But nothing comes for free, so learned alpha usually tends to be quite large. And if it's quite large, so our L2 constraint is very relaxed, so let's use it mostly as an upper bound. But if we are fixing alpha to a small value, leaves our hypersphere a small radius and less surface to spread this centroids for different classes. So if we can assume the number of classes equals to k is equal to k, and if this k to be lower than twice the representation of dimension n, so k is less than 2n, so we can distribute the classes on a hypersphere of dimension n in such a way that any two class centers are at least pi over 2 angles apart. And even more, some two classes would have even pi angle between them. And it would lead to our probability, softmax probability, so we can find out this quite simple formula. When the pi over 2 angles apart, so it would have would provide us the cosine of pi over 2 would give us 0. So here we have k minus 2 e to the power 0. Also initial one e to the power of alpha, but as I said, like at least two classes would would have this angle of pi, and here we have cosine of pi is -1. That's why minus alpha. So yeah. This is we can omit this term, and this is approximately equal to e to the power alpha over e to the power alpha plus k minus 2. So the lower bound, in order to have some allowable, for example, we would like for the accuracy to be, for example, at least 1/2. Is alpha low is equal to logarithm of p multiplied by k minus 2 over 1 minus p. In practice, fixed alpha closer to alpha low is preferred for small data sets, but for larger data sets, it's more close to the learned alpha. Okay, it was very simple. We just normalized the representation. Okay, let's do it a little bit further. So consider the case where we do not have the bias term. So we are just doing argmax over I in the set composed of 0, 1, etc., k minus 1, or the dot product of wi and h of x. So we do not have here this term. And the simple proposition here that I would propose for you to prove that for any s greater than 1, the maximum value of over I in the set composed of 0, blah, 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 k minus 1 of this softmax probability is greater than or equal than this maximum probability of usual softmax, and here we are just using the initial h of x, and here we are using this adjusted representation. So we just multiply here, as this is a scalar. scalar greater than 1. And if we just multiply the representation by this scalar, for the biggest probability, its probability even becomes bigger when we multiply by s in comparison to the initial one. Yeah, this is what I just have said. And the proposal here, addition proposal, let's normalize both projection wi and representation h of x. Remember, previously we just did it only for hx by some scaling factor L. So h prime of x equals L h of x divided by the norm of h of x, and w prime I of x is equal to L multiplied by w I of x divided by the norm of wi of x. So in this case, the norm of h prime would be L, and the norm of wi prime I also would be L. So at the same time, remember neural collapse. That's why we had this slide a couple of slides before. So for the neural collapse case, the lower bound for softmax loss with normalized projections and representations is this value. So our loss would be greater than or equal to the logarithm of 1 plus chi k minus 1 multiplied by e to the power of minus k over k minus 1 multiplied by L squared. Yeah, that's quite non-trivial but still simple proposition, so please try to prove it, or at least you can consult the initial paper. There is a proof there. Okay, what about the training? So taking into account these propositions, it really makes sense to put as much as possible into this norm of L. Also, finally, when we omit bias term B, we could have the training procedure as close as possible to the testing procedure with the same similarity function S. So again, we don't have here like plus B or something, so we have S here, and this S here is very similar to, again, just simple dot product of wi and h of x. And the final proposal here is not to fix a large L, but to have the single parameter S is equal to L squared, and this parameter to be a learned one. So the final loss is the following. Again, just softmax loss, but we have here the S, and here S, and here we have prime, W prime and H prime as normalized versions. I think it was one of the first papers that introduced this letter S, and everywhere else after that everybody would be using this letter S. One more interesting paper, which is called COCO loss, is based on the centroids concept. Suppose we are using the scaled representations, again, remember h prime of x, alpha multiplied by the normalized representations h of x. The idea here, instead of using learned wi, and remember that in the neural collapse case, wi tends to be as close as possible to the center of representations. So let's use the corresponding normalized centroids. And here, like Cj is a normalized centroids, and C prime j, no, Cj is just centroids, and C prime j is a normalized centroids. And this is just complicated notation how to use the different examples from different classes. Here we are using this Kronecker delta function, delta j yi, which basically means that if yi class is not equal to j, we have 0, but if it is equal to j, we have 1. So we just centroid itself, and then we're just normalizing it. And Coco loss, as I said, we have, for example, for this neural collapse 2020 year, but it was already used here, this idea that the centroids would be concentrated around the classifier. And here, remember, initially it was W. WYI in this case. Oops. Yeah, but anyway, this loss is very simple. Again, minus 1 over m, the sum over I from 0 to m minus 1 of logarithm of the correct probability, correct just exponent divided by all the other exponents, including this one. And exercise here, again, you can try to do it by yourself, or you can consult the paper. So suppose we have the upper bound for the Coco loss as epsilon. So we can prove that the lower bound of alpha is equal to 1 over 2 multiplied by the logarithm of k minus 1 over e to the power of epsilon minus 1. Okay, so we looked at the initial softmax losses and its improvements based on some normalization. Okay, let's move into the second area of research, which is called metric learning or Euclidean metric loss. The goal here is to increase interclass difference and to decrease intraclass variation. Variance based not only on probabilities and not at all on probabilities, so we don't care about probabilities. We are concentrating only on the representations, or as it's called in the FaceID world, on the embeddings itself. Examples are DeepID2. Remember, we had DeepID in the initial, on some of the first slides, but for the second version, they already used the metric loss, or more specifically contrastive loss, or FaceNet, very famous paper from 2015, which used triplet loss. And yeah, the idea here is to make this interclass difference, D12, greater than the maximum intraclass variations, D1 or D2. Yeah, and make here this class separation. Okay, what is interesting that initial application of metric loss to face recognition task was done in 2000s, in 2005 and 2006 by the classic of deep learning, Yan LeCun. So, but at that time it was not Face ID, it was face verification because the task was simpler, and at that time the resources, for example, computing resources, the data sets were not so big, so face verification was quite reasonable as a task at that time. And labeling, the notation for labeling was used Yij, and if Yij equals 0 means that the pair of faces xy and xj from different persons, but if Yij equals 1, it means that pairs of faces xy and xj are from the same person. And the measure of like closeness, similarity, in this case, it isn't, for example, as for the previous slides we have seen that it is dot product. Here is the Euclidean distance on top of face representation, so just norm of the difference between h of xi and h of xj. Yeah, but if these, for example, representations are normalized, it is almost the same up to some coefficient to the dot product. Empirical observations that have been done during this initial series of works. First of all, we need a sort of hinge laws for different IDs. So we don't need to make the representations of different IDs go into infinity. Just it would make the whole algorithm unstable. Also, vice versa, we don't need hinge laws for the same idea, because otherwise representations will be just concentrated around some margin, around some, for example, sphere. And the last one observation here, so we need this margin. We just not need to push as far as possible, or push or pull as close as possible. We just need some margin to have some non-trivial representations. Otherwise, there could be some collapse, for example, to 0. And this is what is called max margin contrastive loss, or MML, or MMC. Denote as m lowercase. This is not the same m which we used before as a number of samples. They're different. The margin for negatives. And when we are talking about negatives in case of FaceID, it means that for different person IDs. Negative pair of faces. And the final loss for the pair xi xj is LMMC, MMC, of xi xj is 1/2 yij multiplied by sxi xj squared plus 1/2 multiplied by 1 minus yij multiplied by maximum of 0, minus m minus s xi xj and again squared. Yeah, and you can just, we either have the situation, because remember, yij is either 0 or 1. So we have here situation or here. And it's quite similar, remember, to binary cross entropy. So we also like have one formula, but basically speaking, it is two formulas for different use cases. Either we have this term or this term. So when we have, so what is the idea here? When we have the images of the same face, we would like for them to be as close as possible, and ideally to be the same representation vector. So we're minimizing this term. But if they're different, of the different person IDs, we would like for them not to be as far as possible. We would like for them to be just bigger or greater than m. So we don't need for them to go into the infinity. In this case, we would have just unstable training. And if they are just out of this sphere of the radius m, we will be okay. And this is hinge loss. Yeah, and this is illustration. So we have our x, initial, it's usually called anchor, and here it's denoted by the star. And we have the similar images, for example, of the same, not person, the same object in this case. We would like them to be as close as possible, and ideally to be here. But if we have the representations of different objects, we would like to them not go to the infinity somewhere here, just to go a little bit around this area of radius m. And yeah, there is also some modification which is called marginal loss. It's just a little bit different formula, but usually, basically speaking, the same idea is here is used. Here we have one nonlinearity with two margins. Previously we had only one margin, m, but here we would have two margins, psi and theta. Here, as you can see, here we normalize the representations and have the square root of the, or not square root, just square of them, of the difference of them. And we would like to be not bigger than theta, and also here the psi. And again, but here a little bit different notation. As previously for the contrastive loss we used Yij either 0 or 1, but here version either +1 or -1. So +1 again the positive pair, it means from the same idea, and -1 from different ideas. And theta threshold for distinguishing whether representations are from the same class here. And psi, this is error margin for the classification hyperplane. So just added here just additional parameters. Previously we didn't have additional margin for the how to say, for the differences of normalized representations for the same class. But here, yeah, we have here and we have here the second one. Yep. What we have looked at before, it was absolute thresholds, absolute, I don't know, comparisons for contrastive learning. So we concentrated on pairs, positive and negative, and these distances as well as thresholds are absolute ones. But in fact, what we need for every input representation, which we call anchor, to be just closer to the positive embedding than to the negative one. So we care about relative difference of distances. And this is the illustration of it. So just anchor, we would like for the positive to be closer than the negative. We do not want to have, for example, here the absolute absolute distances for each anchor. For example, for anchors of different classes, these thresholds can be different. We just what we would like to have, we would like to have the relative, the correct relative ordering. So positives have I don't know, the distance which is less than negatives. That's all. And so this is the idea that what has been used in FaceNet, and this is a super I don't know, valuable thing that has been introduced in this FaceNet paper. I really encourage you to read this paper. It is nicely written in 2015, and the concepts of triplets was used to define the triplet loss. And what we can see here, this is the sum over all training examples, maximum of 0, and this is the most important thing. So we have anchor, and anchor, this is our input. For this anchor, we have a number of images of the same face, of the same person, or not of the same, of the same person ID. This is what we call positive. And we have a number of images of different person ID, which we call negative. And what we would like to have, we would like to have that the distance between anchor and positive to be not just smaller than the distance between anchor and negative, but to be smaller with some margin alpha. So yeah, this is input phase, positive phase, and negative phase. all representations are normalized, so the norm of each h of x is equal to 1. And alpha is some hyperparameters, and in the paper the authors used alpha which is equal to 0.2. But how to find out which should be used as a negative? So this is crucial, how to make this triplet selection process. And actually we have three types of triplets. Easy triplets, where we have triplets with zero loss. In this case, we have distance between positives plus alpha is less than distance to negatives. So everything is nice, loss is zero, we do not optimize anything. So we are already in our target domain. Hard triplets, which triplets that were used for FaceNet. So triplets where the negative is closer to the anchor than the positive, and so no any alpha, as you can see here. Just distance between negatives is less than the distance to the positive. But we also have this gray zone, or which is called semi-hard triplets. Triplets where the negative is not closer to the anchor than the positive, but still having non-zero loss, because the negatives are bigger than the distance to the positives, but less than positives, distance to the positives plus alpha. And here is the illustration of it. So you can see here the hard negatives, which were used in FaceNet. The easy negatives, that everything is cool. And this semi-hard negatives, this is margin of the length of the distance alpha, which is also sort of gray zone. We can use it or we cannot use it. This is also the equation to the implementation of the algorithm. It's up to you if you are going to use the triplets in your task. Later, a very simple idea has been proposed. Let's use triplets, for example, but even if the model hasn't been trained with triplet loss. What we are going to do? Let's learn the projection T, projection matrix, so as it projects the initial representation into the H prime, the new representation, and on the H prime we are going to run the so-called triplet similarity embedding loss. As you can see here, this is again alpha plus the similarity to the between negative and anchor, and minus similarity between anchor and positive. And please look at the sign here, plus and minus. Recall that for distances we have minus distance plus distance, but please don't be afraid, this is the same, because how to say, distance something like minus similarity. So the bigger similarity, the less distance, and vice versa, and that's why we have here the different signs. You can just look here. Plus for positives, minus for negatives, and plus for alpha. And here we have plus for negatives, but minus for positive, and again plus for alpha. Or you can even try like the very simple here binary classification, even loss between positives and negatives. Because although it is written in the form of softmax, but basically speaking, if we divide the numerator and denominator by the numerator, we would have this binary cross entropy. And it's called triplet probabilistic embedding, TPE or TSE, which is interesting. Both these two papers have been written by the same set of authors in 2016. Although they are quite simple, very simple and beautiful ideas. Just in practice, they're quite unstable to train. Unfortunately, it was like my personal evaluation of these papers. But sometimes they help. Center loss. The idea here is to reduce intravariance, and additional loss term here is called LC, which is 1/2 multiplied by the sum over I from 0 to m minus 1 of the norm of the square norm of the difference of h of xi minus c yi, and cyi, this is the centroid for the correct class, for the class xi. Yeah, centers, again, remember neural collapse. The centers can be initialized with wi and updated just later with the fine-tuning process. And remember neural collapse, remember Coco loss, and everything from this idea. The final loss is just usual softmax loss plus some coefficient lambda multiplied by this additional loss term, LC. Yeah, and these are just illustration. For example, when we have very low parameter lambda, just usual softmax loss, but when we increase and increase, it really starts to concentrate around some clusters, as you can see here. And again, this is from NIST, I guess. Yes, these are digits from 0 to 9. Just because we would like for every h, for every representations, to lie near its centroid. But basically speaking, in the neural collapse case, we don't need this term because it should be done at the end. But just because we are not in the over-parameterization regime, we need somehow to help, probably. Yeah, and just again, some quite beautiful comparison of different losses that we looked before. Softmax loss, triplet loss, you can see there on the sphere because we normalize the representations in just different areas on the sphere. Just central loss without softmax. Okay, so this is when we don't have, we only have LC. Still looking somehow quite randomly, but when we add in softmax, it just tries to push them against each other. And this is Coco loss, although it's also has used this usage of centroids. It's still, how to say, not, for example, separate areas. They still intersect in the origin. So it's quite interesting, to be honest. So softmax are just different, like I don't know, big and broad beams. Triplet loss is just areas on the sphere. Center loss with softmax are just some blobs, but at least they are not intersecting in the origin as softmax loss. And Coco intersects in the origin, but they are like almost straight lines. They are not blobs. Okay, also the imbalance problem is very crucial for the real-world data set. What does it mean? It means that for some classes we do not have enough data. And a couple of adjustments for this imbalanced data sets called center invariant loss and range loss. Center invariant is CI and range R, denoted by these letters. So the center invariant loss idea is to normalize implicitly the class centers. And it's done by additional loss term to center loss. And when talking about range loss, we here like two ideas: the minimize intraclass volume and maximize interclass distance. So this is about the volume, quite sophisticated formula. The sum over I equals to from 0 to k minus 1 of R over sum of sum over j equals to 1 to r of 1 over dij, where dij is the jth largest pairwise representation distance between inside class I. Usually j is equal to 2 or 3, not that big, so only 2 or 3 biggest pairwise distances I used, but doesn't matter. It just how to say, minimizing the intra-class distances. That's why, for example, if we have very big d, it seems that we have smaller these fractions, and the overall fraction is also big. But our loss needs to be minimized. That's why we are minimizing these largest pairwise representations. Why not using, for example, d without this two different layers of fractions? I'm not sure. Probably I need to read more carefully the initial paper. And interclass is quite simple, and again this is hinge loss as in contrastive loss. So we would like for the difference between different centroids of different classes to be not less than m. So we would like for this, for example, let it be this square of the norm of difference of cluster should be and this is the loss for this how to implicitly normalize the class centers. So we have the Cj the class centers. So what we are doing, we just trying to find out this average of their norm, and then we are just doing this minus with the current norm of the current centroid, for the current centroid. And in this case we are providing for all the class centers the same norm, and you can see here. So if we are outside of this norm, it's pushing from outside to the surface, and here from inside to the surface. But unfortunately, there is no how to say specific radius in this case. Okay, and the third and one of the most important approaches here that are called angular loss. Here the goal to perform the separation not in Euclidean space of embeddings, but in the space of embedding angles theta. And some well-known examples here are L softmax. Please do not mix with L2 softmax. It's very different, as I said before. L softmax, A softmax, or sphere phase. These are synonyms. And AM softmax or cos phase. They are synonyms but different papers, which is quite funny. They have been published at the same year, probably in the same month even, from different authors. And this is the illustration. So this is original space, and this is how usual classification across entropy loss, softmax loss is working. But what we would like to have, this separation based on the angles. So sort of angular bisector between two sets of points, this yellow ones and this magenta ones. We need here to project onto the sphere in order to use this angular separation. Okay, let's start with the L softmax idea. I would say the L softmax is the one of the most important paper because it provides a lot of insights that were used afterwards. Again, let's omit bias term. We already did it, I guess, for norm phase. And reformulate the logit. Logit Li is equal to dot product of Wi and h of x. And again, dot product is a multiplication of the norms multiplied by cosine of the angle between these two vectors Wi and h of x. And this theta I is in the closed interval from 0 to pi. And this is the angle between this projection vector wi and representation h of x. In this case, softmax loss becomes like, yeah, just yeah, and I think like we need here. Oops, sorry. Yeah, I missed it. And we need to sum over the whole training data set. This is our... no. I'm correct here. Because this is the softmax for xi. And for binary classification with the correct class 1, the original softmax forces the following. Because we have the binary classification, this is the linear classifier, and just dot product of w1 and h of x just be bigger than the dot product of w2 and h of x. That basically means of, let's use this, I would say, derivation of dot product into the multiplication of norms and cosine, and we would have this. Quite understandable. And the idea, let's do the task even harder, not just using cosines, but for the biggest, the correct class for cosine m multiplied by theta 1 and m some natural number. And also theta 1 is in the closed interval from 0 to pi over m. Why it is needed? Just because to have this monotonicity, and which monotonicity will show here. So in this case, if we have this, we'll automatically get the needed initial. So this would lead to here. Why? Just because cosine. Let me depict it here. Here 0, here pi over 2, and here pi. And we can see that the cosine function of in the closed interval from 0 to pi, it's just decreasing function. So when we are using, when we multiply theta by the integer, not just integer, but the natural number, which is, for example, greater than 1, it just jumps from, for example, this point to this point. And it means that we have really, the value here is bigger than the value here. And that's why we would have here m cosine theta 1 is bigger than cosine m theta 1, and at the same time we already have it by definition of our loss. This is cosine theta 2. In this case, if we can get this, we would have this, but at the same time we need to be careful about this thing. In order, why we need this constraint? Just because to be, when we multiply, for example, here we multiply by m. When we multiply by m, we will still need to be not jump out of our initial closed interval from 0 to pi. That's important, and a lot of work, and you'll see it, is concentrated around this, how to deal when you jump out of this pi over m. Okay, and the new L softmax, which is abbreviated as LSM, is illustrated here. This is the same as it has been before, with the only difference. So we would have here this xi. What is xi and why we are using this xi? First of all, when we have this initial interval for theta, we would like to be cosine of m multiplied by theta, this m. This is our initial idea. This one. And if outside of this region, when theta is in the left open interval from pi over m to pi, it is equal to some function d capital of theta with this is the constraint for this psi to be continuous. So at the left point of d of pi over m, it should be the same as cosine of m multiplied by pi over m. So basically speaking, cosine of pi, which means -1. And yeah, it should be still monotonically decreasing function. In order for it, again, when we just jump lower, when I'm doing this multiplication, still to be to have this how to say to have this inequality satisfied. And authors just propose to use the following form of this function psi of theta. It looks complex, but it just creates the cosine, 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 etc., etc., etc. But this is the theory, but in practice usually it's not everything works as in our ideal theoretic case. Authors provided the relaxed strategy from like iteratively and continuously moving from vanilla softmax to this L softmax, gradually reducing the parameter lambda from a very large value. They started from 1000 to a small value which they used 5. And they used this formula. You can see that when lambda is very large, so in this case we would have it just dominates, this term, it just dominates everything. In this case we would have just cosine. But when lambda is small, this term should also be important. So we are moving between cosine theta to the cosine of m of multiplied by theta. Yeah, and this is just illustration of this psi of theta for softmax loss in just really cosine, and this is the red one. This is theta psi of theta for L softmax loss when we have m equals to. Again, you can see here they just have this this part of the figure and then copy paste it here. L softmax and decision rule. It's quite interesting and important here. Suppose the norms of projection vectors are the same, so the norms of W1 and W2 are the same. So in our case, the initial softmax rule, this linear classification rule, is just theta 1 is less than theta 2. For case where the norms are different, is a little bit more complicated, so you can refer to the paper, but generally speaking the same. The results are the same. For the L softmax case, it means that m theta 1 is less than theta 2. For the when we just switch in the classes, this is the same. So m theta 2 is less than theta 1. Suppose that alpha is the angle between these two classifiers, W1 and W2. It leads us to the following. So decision boundary for the class 1, we just not less than, but equals to. And at the same time, we have, for example, for this theta 1 and theta 2, they are both constitutes together the initial angle between W1 and W2. So we have here the system of two linear equations. And we can find out that theta 1 here is just alpha multiplied by 1 over n plus 1. The very same we can do for the second class. This is symmetry. We could have alpha multiplied by 1 over n plus 1. Just note, by the way, the decision boundaries are different for different classes. For softmax, the decision boundary is the same for if the classes just have the I don't know, separating hyperplane. This is the same for class 1 and class 2. Here they are different. They're different, as you can see here. This one and this one. So what does it mean? It means, for example, this is initial alpha, W1, W2, and this is theta 1. This is the separating hyperplane, and this is for the second class, theta 2. So, and these are two different, because for softmax it would be just this, first and second class. And decision margin is alpha m, which is equal to alpha minus the sum of theta 1 and theta 2, and it is equal to alpha multiplied by m minus 1 divided by m plus 1. So, for example, if we have initial angle between W1 and W2 equals 180 degrees, in this, and m equals to 2, in this case, we would have the decision margin is 60. Or yeah, like very simple here illustration. W1, W2. In this case, it just alpha margin. Yeah, just recall, this is margin. This is almost the same, like conceptually the same as we are having inside the support vector machine case. And we also have the margin, but this margin is not in the angular space. It's in usual feature space. So, for example, class 1, class 2. And this is the margin. This is how SVM works. Yeah, this is the illustration. Yeah, here theta 1, here theta 2, and this is margin. Yeah, and some not definition, just abbreviations mostly. So let's jump into a softmax, and again let's talk a little bit about normalization. Explicitly normalize projection vectors wi to 1 and 0 biases bi equals 0 for all I. It is called modified softmax loss. So this is what is modified SM. Modified means that we are doing this normalization and removing the bias. When we introduce the angular margin and theta, this is what is called a softmax, a SM loss. For the binary case, maximum intra-class angle is can be calculated as alpha over m minus 1 plus alpha over m plus 1. I would keep it for you, just in sort of small exercise. The hint depended on whether the representation is lying inside or outside angle alpha. And we already calculated the minimum interclass angle is alpha inter, or alpha m, equals alpha multiplied by m minus 1 divided by m plus 1. And you can, for example, using this and this, you can replace with this and this, and you can find out that m should be greater than or equal to plus square root of 3. but we know that, for example, m is integer, not integer, just it's natural number. Square root of 3 is 1.7 something. So basically speaking, m should be bigger than 4. Should be greater than or equal than 4. This is for binary case. For multi-case, we can prove that m should be greater than or equal than 3. And yeah, this is also like some small exercise to prove it. The hint is to use assumption that wi have the uniform distribution, or you can just try to do it by yourself, or you can consult the original paper for it. But it doesn't matter. So yeah, we have here, so m should be something like 3, 4, or even bigger. And for experiments, usually makes sense to use m something like equals 4. And this illustration, this is usual margin loss. This is a modified softmax loss when you just normalize it and remove the bias term. This is a softmax loss when we have this m as a multiplying factor for theta. And this is a softmax when we have both this. So remember that for L softmax we didn't have this. Didn't have these normalizations. So we added it for A softmax, or it's also called sphere face, I guess. Yeah, sphere face. But this is the synonyms. This is all from the one paper. And you can see here, like introducing bigger m, we can have the different more and more align positive and negative pairs. This is this distribution, the histograms of pairs. This is the angles, x, I think it's radians probably, and x-axis and y-axis the number of pairs. And we can see that for negatives, it becomes the distance between distributions bigger and bigger, like even starting, I guess, from m equals to 2, but mostly visible for 3 and 4. So usually 3 or 4 are used. And we can see here, like for m, like for usual a softmax, what a softmax in case of m equals to 1 is just modified softmax. In this case, it would be here. And here the separation is beta, and here even beta and beta. So you can see here, for example, these and these areas for different persons' ideas can be separated. Yeah, but we just had this multiplication factor. What about using quite similar but still different idea, which is called additive margin softmax idea? Add margin, but additive, not multiplicative, and outside of cosine. So psi of theta is cosine of theta minus m, not inside. And normalization, normalize both representations and projections, and scale both of them to L. So S is equal to L squared, and is equal to multiplication of the norms. In this case, the loss again minus logarithm of just usual terms, only S here and psi. Everything else is just the same. In practice, authors used S equals to 30 and M which is equal to 0.4, and no any relaxation strategy. So no hyperparameter lambda. And that's quite important, because here is, let me just yeah, this is it's quite unstable training still. So we would need to gradually move from theta to m theta with this lambda, and this is L softmax and A softmax. They also use the same, but finally we don't need it. So when we put out this this hyperparameter m outside of cosine, we don't need to do it. We don't need to move from cosine theta to cosine m theta. Yeah, and this is how it looks like. This is like different cosine, 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 but these AM softmax, this is the green one here, and this is just the initial cosine, just moved lower by 0.2 or 0.4 or 0.4 minus 0.4. Cos phase. This is the very same idea of AM softmax, but I guess from the different different authors, which is quite interesting. The surname is the same, Wong, but the name is different, and the same year, quite the same idea, but with a little bit more theory. So the lower bound of softmax loss is this one. I think we also did it for the norm phase. Also there it was L squared. So we can find out the S, the lower bound of S. And bound for cosine margin, this is additional term. This is from 0 to k over k minus 1. And just the exercise to try to prove it, and here like the idea which can be used, this one. Again, you can try it by yourself, you can refer to the paper. These exercises are not that complex, usually they're just 1/4 of the paper or even less, for example 1/8 of the paper. And we can see here like this is from basically speaking from 0 to 1, and in practice m equals to 0.35 is used. Yeah, and here is an illustration how different losses just try to push different classes. For softmax, we even, for example, if we have the how to say axis as cosines, the classes just overlaps. For normalized softmax, we have the clear separation, but still no margin. For 8 softmax, when we have the axis as theta, not cosine, we would have this margin, but still this margin becomes smaller and smaller when we go to the origin. And for this cos phase, when we have cosine as axis, we finally have the margin like an SVM here. And remember, this is an M. What is interesting, these are still not theta 1 and not theta 2, because usually we are working and trying to represent and put on 2D plane, for example, using not cosine based axis, but just original axis. So, and it was fixed with the latest work, which is called arc phase, which is the best of all angular losses. It's probably the most successful implementation of angular loss idea. And what is much more important, the authors provided this pre-trained model like publicly, and I guess you can still just download it and use it in any application where you need, for example, FaceID. And it just democratized the FaceID task a lot since 2011. Yeah, and it just uses everything that we used before, just normalization for the representation. Basically speaking, just x, it's just h here. We also normalize the classifier w, also doing this scaling s, which is equal to L squared, the same softmax loss across entropy loss, but here again different cosine adjustment. We already had cosine of m theta, we had cosine of theta minus m, and now, surprise, surprise, we're having cosine of theta minus m or plus m, doesn't matter. Yeah, we could have 3 different combinations, and finally we have here the third combination. Yeah, this is the idea. And in practice, m equals 0.5 is used. And arc phase loss, again, very similar, again s, and again psi here. In practice, s, which is equal to 64, is used. And we can even do better and further. Let's combine all margins. And so we could use psi of theta as cosine of m1 multiplied by theta plus m2 and minus m3. Yes, all 3 ideas. Cos phase, sphere phase, and arc phase. Sphere phase, cos phase, arc phase. All 3. By the way, let's provide, this is sphere phase, this is arc phase, and this is cos phase. And everything together is called combined margin loss. And you can see that for this combined margins, the abbreviation for this CM, 1 or 2, it's not that big difference, to be honest, in comparison, for example, to, I'm not sure, for example, green one, which is cos phase, or arc phase. Everything is very close. But it turns out that this psi having a lot of importance on the training procedures, on the stability and convergence of the procedure, and on the final performance as well. And finally, as I said, for the arc phase, what we have the usual margin as an SVM for usual axis. For cos phase, these classes are sort of not linear. For sphere phase, we have this margin, but it becomes smaller and smaller. For softmax, we don't have it. So yeah, finally, we got it. And let's finish. Let's make some quite important notes for this lecture. First of all, representations that are learned are one of the most valuable outcomes of deep learning and neural nets in particular. So originally this feature extraction of feature machinery has been used. It was mostly like manually driven, even in the automatical, and even if it was done automatical, it wasn't not so smart. But when deep learning came, the whole idea of deep learning is to create these separable representations, and on top of them, usual softmax or something similar. And yeah, given this correct representation, the final classifier is, surprise, surprise, just a usual linear discriminant function. We don't need anything, I don't know, super mega cool. We're just using usual SM classifier. But in order to use it, we need to provide representations that can be separable. And this is the overall task of representation learning. And yeah, normalization of both representation and projection vector that maps representation to logits is important. So we need to normalize. Metric learning, although it's very beautiful idea, it's quite nice and understandable, but it's not really stable. But probably it's inevitable, for example, for contrastive learning without labels. For example, when we do not have labels, like an example right now, we have a lot of works, not only for computer vision, where we have a lot of examples in the training dataset without any labels. But what we can do, we know some process, some parameters of the process which is called augmentation. When we adjusting input a little bit by some rule, so as the output of this transformation is still the same object. For example, we're adding some more contrast or more noise or some blurriness or something like that, but we still have the image of the same object. And we are doing it in this training in the contrastive manner. For sure, we can also apply some additional adjustments. For example, softmax for the portions where we have the labels, which is called right now SSL, semi-supervised learning, the big directions, and probably this is one of the important approaches in the real world, because usually in the real world you could have a lot of training examples, but either without labels at all, or with some labels which are noisy, or where we do not have enough labels. We only have labels for 1% of your data. So it's still inevitable. And Angular-based margins now are the major and dominant forms of separation for representations. And this is Angular analogy of SVM, and probably some of you who remembers the original ML, SVM is the best single, not as ensemble, but the best single classifier in machine learning, I would say. And here, like in the deep learning, it seems like Angular base is the analogy of it. Also, yeah, we have looked into the FaceID task, but to be honest, a lot of different task directions are using right now Angular-based losses. This is not only about FaceID. This is about, for example, how to recognize places when we have 1 million of different places, like sightseeing, etc., etc. And last but not least, overview in the historical perspective, when we can look at some established task, but very complex task, because FaceID initially was a super complex task. No any method in the beginning been working in the real world in significantly good manner. Yeah, but so when you have this evolution, you can better understand the reasoning behind these design choices. Why we have this normalization? Why we have this dot product? What is the reason behind margins? Why, for example, we need centroids? What is the connection with this neural collapse, etc., etc. And that's, from my point of view, from my subjective point of view, one of the best use cases when you can year by year just track the progress and to understand how loss functions and representations can be constructed from the very beginning until the end. Thanks. Thanks for your attention. Bye.